Understanding magnetism is all about understanding the relationship between a magnetic field and a moving charge, and those relationships go in all sorts of different directions. And so today we're going to talk about how moving something through a magnetic field can actually create a current, can induce a current. Um, and that is governed by Faraday's and Lenz's law. All right. So now we're going to deal with, I'm going to push this symmetry on you some more. We've seen that a moving charge creates a magnetic field, right? And that movement is the root of all magnetic fields. We can put this in terms of fields, not just in terms of charges, so that we can say a changing electric field creates a magnetic field, and that the inverse is also true. A changing magnetic field creates an electric field. And that's going to become more important to us as we think about the practical uses of a magnetic field. This is that's the heart of that symmetry between electric and magnetic fields. So let's think about how that is. How do we create an electric field? In other words, how do we create a current with a magnetic field? So imagine we have a uniform magnetic field, which is what this image is over here. Those X's are the magnetic field being pointed into the page. If I take a neutrally charged conductor and I move it through this space, there are electrons in here, right? Charged particles that are now moving in relation to a magnetic field and moving, importantly, perpendicular to that magnetic field. So there's going to be a force. And that force is described by the Lenz force. And if we think about it, we can figure out what direction, right? We have electrons in here. Our fingers go into the page. Our thumb points in the direction of velocity. And the force on a negative charge is from the back of our hand, and it's going to be downward. And so that's going to push our negative electrons down in the bar. So we're going to have a polarized bar now, right? Where one end has a negative charge and one end has a positive charge. So that's pretty cool. And we've got that polarized bar. So what does that mean? That doesn't give us a current, right? That just gives us a polarized bar. So that means there's a difference in charge, uh, and we've given the bar an electric potential difference or a voltage, right? Because we have a bunch of positive charges here and negative charges there. And we can also call our voltage an EMF, what's called an electromagnetic force. Um, that's created because we're going to pack a bunch of these electrons down here, right? The magnetic force is pushing them that way. Their hatred of each other is pushing them back this way. And depending on how fast we move this, those two forces are going to balance out. Magnetic pushing them down, repulsion pushing them back away. And they're going to reach some kind of steady state where they stay in one place if we keep the bar moving at the same velocity. We can balance these forces. That is, here's the force of repulsion amongst the gathered electrons. Here's the Lorentz force, and we can figure out what our electric field in that bar is. It has to do with the strength of the magnetic field and the velocity that we're moving that bar. The faster we move the bar, the larger that electric field becomes. If we stop the bar, what happens? Well, those electrons are going to rush back to the rest of the bar because they don't want to be hanging out with each other because they hate each other. Okay? Now we're going to make something out of this. We're not just going to have a nice little bar that we're moving through space polarizing. We're going to connect it to a couple of metal rods here, or not connect it, but lay it on some metal rods, out of which we can make a circuit. So we'll have a nice little circuit going through here. Um, as I move this bar, it's going to create a voltage from here to here. And those electrons that hate each other, they can't go that way because the magnetic field is forcing them this way. But they say, I can escape. I can run along this way, right? Or, well, again, that current thing about being backwards. The electrons are actually going to run this way, but we call the current going that way. Okay, so the electrons get forced down here. They want to get away from each other, and so they go in that nice little circle. And that's how we create a current, by moving a loop essentially through a magnetic field. And we can determine what that EMF is, what that voltage is, because it has to do with the length L between the two, basically the length of our rod, the strength of the magnetic field, and the velocity. And we can put this in a whole bunch of different forms here. One of those forms turns out to be important, and that is B times delta A times delta T. Delta A is, you can see that this is sort of velocity of the bar here, right? The faster the bar moves, the faster my area, that is the area in the loop, is going to change over time, right? B times delta A is something that we call magnetic flux. That is how many magnetic field lines are going through our loop. That's what flux is. And magnetic flux helps us determine what our EMF is according to Faraday's law. And this is an important law that defines how much voltage we can get from a situation like this. And it has to do with the number of loops you've made, with the flux, or the change of flux, that is how much different is the flux one moment as opposed to the next, divided by a change in time. So how quickly are we changing the flux in our area? If we don't move the bar, the flux stays the same and we have no EMF. But if we move the bar quickly, the flux is going to change very quickly and we'll get a strong voltage. That's Faraday's law. And this is an example of what's called induction. It involves creating an electrical field by changing a magnetic field. And one example of this, and you'll actually do this in some form or another in our lab, but the classic physics lab is you move the magnet through the loop of wire, right? Well, what are you doing? You're changing the amount of flux through that wire, right? I've got a bunch of flux when my magnet is real close to it. I pull that magnet away here, and I'm going to have less flux going through there. But if I don't move it at all, I have the same amount of flux. Okay, so it's key that the magnet, something has to be moving, right? In order to have a change in the flux and to get some kind of voltage. The faster we move that magnet, the more EMF we're going to get, the more voltage and the more current we're going to get. So the last thing we want to talk about is a sort of tweak to Faraday's law called Lenz's law. When something moves the charges in a wire, right? So if we move that bar through the magnetic field, those electrons have to be moved, right? Something has to accelerate them. So we have to have a force. So we have to have something doing work. What is the force of that? Well, the source of it is the work that's done in pushing the magnet against the magnetic field that's created by the current. You want to think through that one again? It's not easy. But essentially what's happening is the current is creating a magnetic field that's trying to replace what was lost. Okay, so if I push this magnet this way, by pushing these field lines through that loop, I'm increasing the flux in the left to right direction. Well, the induced field is going to try and create flux that moves in the other direction to return it to the state that it was before. Similarly, if I move this to the left away from the loop, I'm reducing the amount of flux through the loop, and the induced current is going to try to create some flux that balances that. So the coil's induced field pushes back against the magnet. And that's actually what's moving your current. That's really strange. We'll try to talk about through that in class because it kind of hurts your head to think about it. What that means, what is Lenz's law in terms of Faraday's law? It's the exact same as Faraday's law, except he added a negative sign, which I hope to do one day, is just to add some strange, negative sign, maybe a fraction. I don't know. Some add something to a fame. Maybe I'll do Newton's law, and then I can have Newton's and Augsburger's law. But so Lenz got away with a nice easy one there. Just add that negative sign. All right, and that is that for this video.